week 4 of Analog Lab. Today we're finally going to use the oscilloscope that you all should have. So what I'm going to do is just demonstrate how this thing works for the first half, and then we're going to get into software called Multisim, which is going to be our circuit simulator for building circuits online. So, a lot to go over today. First, let's talk about this oscilloscope, right? So, this model of oscilloscope was one that I was able to find on Amazon for a relatively cheap model of oscilloscope that we could use in this class. The oscilloscopes that are at the NYU lab are several $1,000s, and this was the one area that was the most difficult for me to figure out how to adapt to doing this at home. So, basically the first thing you should know is that an oscilloscope is a way we can visualize waveforms. So what we're going to do today is look at some sine waves, some square waves, and use the oscilloscope to see how to read them. I have two things plugged in here. I have my power supply, and this says DC 9 volts. I sent you all a 9-volt adapter that should work with this. All I have to do is plug this in, and it will turn on. Then on this side, I have my probes. And I have a black probe and a red probe. And I have just two little wires clipped onto these, because this will be the way that I attach this to my breadboard. But you can see that when this is unconnected, I don't see anything. That's because there's no signal here, so it's a straight line. I'm not going to see anything here. So, first thing I'm going to do is I'm going to go over some things to show you how to play a sine wave. So, this is this week's lab. In this lab, we're going to learn how to use an oscilloscope to analyze audio signals and troubleshoot them, and then we're going to use the online circuit building tool Multisim. So, the first thing is some interesting things to look at on an oscilloscope. And these first three are links. I'm just going to open those up in new tabs. And I'm just going to open them all up separately. This first one is an online tone generator. This will play a sine wave. And if I sweep this, I can change the frequency. I'm going to stop that. And I'm just going to go over these three sites really quick. My white noise generator has already turned on. You can see that I can adjust the white noise per frequency. So if I want to change this to more pink noise or other kinds of noise, I can do this. I'm just going to turn this off for now. And then this third link is another wave generator, but this gives me the option to change this. This volume is pretty low, so you might have to crank it. Sine wave, square wave, triangle wave, sawtooth wave. So because I'm recording on here, what I'm actually going to do is load up the sine wave generator on my phone, because that way I can still talk to you and we don't have to hear 440 hertz playing all the time. If you are like me and have an iPhone, you may need to get yourself this iPhone to headphone jack adapter, which was on the list. Basically, we need a way to get audio from our device into the breadboard. So, switch back to my breadboard view. And I'm just going to slide this over so I can get the breadboard here, right? Also, all this lab, we are not going to use power. So I'm going to unplug my battery clip and just throw that off to the side. You will not be needing a 9-volt in this class. So clean this off entirely. And the first thing I'm going to do is put in my audio jack. Now, you should all have an audio jack. I think yours is maybe a little bit different than mine. Hopefully it's a little easier to work with. How this jack works is there are 5 pins. There are 2 on each of the outsides, and there's one in the center. So when I place this in the breadboard, I want to make sure that each of those has its own row, and I'm kind of going to position it so that I have a little bit of room behind it to plug in wires. Now, when we use these, and I'm actually going to just move it to the top so that I have some space to work with here. How this works with a headphone cable. Headphone cables like this carry 3 signals. There's one signal on the tip, there's one signal on the ring, and there's one signal on the sleeve. You may be familiar with TS or TRS. That stands for tip sleeve or tip ring sleeve. You also might be familiar with TRRS, which is tip ring, 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 sleeve. Newer Apple cables will have a lot of rings because there's a lot of stuff traveling through these cords. Your standard stereo cable is going to carry the left signal through the tip, the right signal through the ring, and the ground for both in the sleeve. So, when I put this in here, how this works is, on the underside, the center pin is my ground. This is shared between my right and my left. My left signal is going to be on this top pin. My right signal is going to be on this bottom pin. The 2 pins in the middle, I guess pin 2 and pin 4, we're not going to use in this class. They basically allow you to do things like have a circuit open or close if something's plugged in or not. They're kind of switches that work when plugs plug in. You can use them later in the semester, but for now, I'm only going to choose the left pin and ground. I only care about mono signals today, so you can use either of the outer pins. They're going to look identical, top or bottom. So, what I'm going to do first is I'm just going to pop that into my breadboard, and then I'm going to take my oscilloscope probes, and I'm going to connect the black probe to the middle, and the red probe to one of the outer pins. Okay? So I've skipped a row in between, right? Let's slide this over. And for the first part of this lab, I'm just going to play something from my phone, and we're going to look at what this looks like on the oscilloscope. So let me just cue up the sine wave. And we'll see what I got here. It's fun when this all works when you test it, and then when you just fire it up, you get nothing. Let's just reset that, and we'll see if I can get a sine wave here. I'm just going to plug my phone cable back in again. Sometimes this does some weird stuff. And let's flip this over, and we'll see if we can get anything at all here. Cool. All right. I'm going to try one other thing. Okay, so just for troubleshooting's sake, this is a little headphone jack that I have soldered to 2 wires. So I'm just going to see if this jack is my problem, just because I want to show you what this looks like. Let's plug in ground to ground, and power to power, and still no signal. So hopefully this is actually my... This is my phone that is the issue here. Hey, finally. Okay, so I refreshed the page on my phone, and that was really what did it. Although it just appeared for a second, my wire fell out here. All sorts of fun tech issues today. Okay, so what I really want to do is just show you this sine wave, and we'll go through and look at why this happened later. Okay, so first thing I want to show you is this CPL switch over here. This is our coupling, and so, oh, it looks like my phone is off, then it will go away. That's cool. Actually, let me just output the little Moog synthesizer over here. This should give me a nice steady sine wave that doesn't turn off. Let's do that. Let's just look at a square wave instead. Okay. So I've got a square wave. It is kind of falling off of the screen. It's a little too big. We're going to fix that in a second. If I switch this coupling switch to the far left, to ground, I will never see any signal. However, I do want to make sure that my line is centered. You'll notice, because I'm plugged into this synthesizer, it's a little below the center line. That's okay for right now. However, if you switch to ground and your line is anywhere other than in the center, you might want to adjust that. So what I'm going to do that is I'm going to use this little button down here to select. This will kind of cycle me through different functions here. And eventually I'm going to light up this little arrow light blue. And then I can use the up and down arrows to kind of adjust where my line is, right? Now, I'm going to put this back to AC, which is what we're going to use for this class. We're looking at AC signals, audio signals. If we switch it to DC, in case there's ever a bias, which means like a DC voltage in addition to my signal, I'm going to see it move up or down depending on how much that bias is. So for right now, we're going to keep this on AC. We should never have to use DC. And then I'm going to go here to my sensitivity 1. So I have 2 sensitivity switches here. And these are kind of like your coarse and your fine adjustment for volts. So right now, I'm at 1 volt per division. And this is pretty loud, right? I think the output of this is pretty big. So even if I switch this, yeah, I have to use my coarse adjustment. If I move this down, it's going to get bigger and bigger. So I'm going to keep this at 1 volt per division, which is all the way at the left. I can also set this to 0.1 volts per division or 10 millivolts. So it looks like this square wave right now is 1, 2, 3, 4, at least 4 volts, maybe more, peak to peak. This second sensitivity is sort of like my divisor. If I divide it by 1, I get the actual voltage. If I divide it by 2, right, you'll notice down here now it says 2 volts per division. This is 5 volts per division. So it looks like this signal, this square wave, is about just over 5 volts. I don't know if you can see it on the camera, but on this oscilloscope, I'm just above the first demarcation line. So our vertical axis here is telling us how many volts the signal is. And down here, this is telling me each division is this many volts. So this is 5 volts up and 5 volts down. Now, coming out of my laptop or my phone, I'm going to be a lot less. I'm going to be somewhere around 1 or 2 volts. So now I'm going to move over here. So basically, I already used these plus and minus. These are adjustments. This top button, if I press it, I'm in hold mode. Notice up here it says hold. And if I press this again, it'll run. Nothing's going to really change for us, but there are some audio signals where you only get a blip every once in a while. If you think about like a hospital, you know, you might want this to freeze every time you see a signal before it disappears. So you would use this to do that. The other interesting thing about this is if I hold this down, then I will get, let's try that again. Nope, I might have to move to a different select. Let's see if this will work. Yeah, there we go. So I just selected the time down here, and then I held that down to get my statistics. So I'm back in hold mode. I get a V max and a V min. So it's 8.25 volts max, negative 8.05 volts min. There's a little bit of a bias here. My peak to peak is 16 volts. It's a pretty big signal. It's coming out of this Moog, so it's a lot more voltage than I'm usually getting. And this tells me the frequency is 338 hertz. So if I just move my my frequency knob on the synth, I should be able to change that. I'm in hold mode, so I'm going to let it run. And let's see. Yeah, so I can adjust the frequency, and you'll see that frequency number move up and down. This is a low-frequency oscillator, so I can't get faster than this. But if you're using a sine wave generator, you should do a better job. So I'm going to hold this down again, just to turn that off. Make sure I'm running. And then I'm going to show you everything I can select. So I already kind of showed you that I can move the signal up and down. This is my vertical position arrow. So this allows me to shift the signal up or down. If I select the time, so right now I'm at 0.5 milliseconds. This is our x-axis. This is my horizontal. So every block is 5 milliseconds. I can change this, and I can make every block, 50 microseconds. This is a lot smaller. I can go the other way. And this is 1 millisecond, 2 milliseconds, etc. Right? This auto, this tells us how to trigger this wave. And triggering is maybe a little confusing, and I'm going to just change this, and I'll show you what that does. So normal and auto are going to look kind of the same. SING, this is actually just going to freeze my wave once I pass the trigger threshold, which I'll talk about in a minute. And I have to actually go back to a different trigger value to get out of hold mode. So basically, when I press select again, don't worry about this for now. This is rising edge and falling edge. This determines whether we're freezing it on the upslope or the downslope. But what I really want to show you is this caret over here. Basically, this is our trigger level. Now, what we're doing is we're saying if the voltage is past this level, we're going to freeze the waveform. So I'm going to move this up, and I'm going to show you what happens if we don't hit this place, right? So see how if my trigger threshold is way up here, I lose the waveform. So triggering basically means when I've past this point on the vertical axis, I want you to freeze the wave so I can accurately measure it. More often than not, you're going to want this right in the middle. So I'm going to move this back down. And once I get below my waveform, you'll see that it freezes again. This will also work on the negative axis. If I go all the way down here, same thing happens. So I'm going to go back to the middle and leave this here. So we should always be on auto triggering. There are other trigger features, but the auto is going to be the least headache for us. You don't have to worry about if this is on rising or falling edge. We're generally dealing with waveforms that they do both. They rise and they fall. So it doesn't really matter whether we trigger on the rising or the falling edge. The last thing I'm going to show you, I'm now selected up here, this little bar. This is my horizontal position. So I can shift my wave left and right if I want to. As far as, horizontal and vertical position, you probably want everything to be at 0 so you can measure things. You might have to move your vertical position if you're not at 0 when you're grounded. So remember, ground first, check your line, and then adjust as necessary, and then flip this back to AC. And I'm just going to, this bottom button, I don't know if you can see that, this is a reset. You can see how it got a little bit messy. Oh, I lost a wire, which that's what happened. Pop that back in there. But if I ever get something messy, I can always reset the entire oscilloscope down here. So, there's also a USB port. I've never used this. I've only owned this oscilloscope for a few weeks longer than you have. So I'm learning what this does. You can power this with these 2 pins if you wanted to. You can plug your 9-volt into some plugs, power it off battery if you want. I'm just going to use an adapter because it's a little bit easier. So, what I want you to do is basically spend the first part of this lab experimenting with your oscilloscope. I want you to open these links, and I want you to look at sine waves. I want you to look at some waveforms. I want you to look at some noise. Play any music. Play any sounds. Just kind of go nuts and look at what stuff looks like on the oscilloscope. Apply some distortion or reverb. See what that looks like. So then, once you do that, what we're going to do is a more specific circuit. So I'll let you play around, and then we'll come back. All right, so connect a cable from laptop or phone to breadboard and connect and turn on probe 1. Turn up your volume, play sine wave. Make a note of everything you do so you see a few waves nice and clear. Guess what will happen if you turn your laptop or your phone volume up and down? Then do that. See what happens. All right, now, we are going to build a circuit. I'm going to actually go back to my phone for this because I think it does a little bit better with the volume circuit. So let me get rid of this and we'll try going back to my normal circuit for this. This is what our circuit is going to look like. Let me zoom in a little bit. Basically, over here is my audio signal on the far left. Notice it says 440 hertz. I am just going to plug in my audio headphone jack and pull that signal from there. And then I'm going to go through a 100 ohm resistor and a 10 microfarad capacitor. And this is the first time we're going to talk about capacitors. So, let's move this over and let's get my parts. 100 ohm resistor. Brown, black, brown for the tan resistors. Brown, black, black, black for blue resistors. And then I'm going to get my 10 microfarad capacitor. This capacitor looks like a little barrel, and one leg is shorter than the other, kind of like an LED. And you might notice on the side of this is this little gray stripe with minus signs. And if you guess that that's because the short leg is the negative leg, you would have guessed correctly. Larger capacitors like this are polarized, so we have to make sure we orient them correctly in the breadboard. So I'm going to remove my probes here, and we're going to come back, and we're going to build this circuit. So I'm going to start with my my audio jack. And the first thing I'm actually going to do is I'm going to take a wire and I'm going to run my center pin to ground. I'm going to use black wire because I want to make sure I know it's grounded. So I'm going to go here, and then I'm going to go to the ground rail over here. Remember, no batteries this week, but I need my reference for my audio signal to be the same reference as my circuit. So grounds need to be connected together. Okay? Then I'm going to take this resistor and I'm going to come out of the top pin and just go into a random row up here. And then I'm going to take the positive leg of my capacitor and meet that and just pick another random row. Okay? So I've got the long leg meeting the 100 ohm resistor here, and now my short leg is here. And we'll go back and kind of look at this. So you see how I went from my signal, which is this circle with the squiggly line in the middle. Don't worry about this symbol. This is the symbol for a sine wave. There's not really a symbol for an audio jack, so we're just going to use this. We're going to go through our 100 ohm and our 10 microfarad capacitor. These two parts, in conjunction together, this is called a DC blocking circuit. Basically, it's going to block any DC voltage from our signal, so we have a nice, clear sine wave. And again, we don't need audio or battery to do this. So now you'll notice there are three little kind of V circles here. There's this green V up here that says part 1 red probe, and then V2 says part 2 red probe, and then part down here says part 1 and 2 black probe, and that's attached to the ground. So I'm going to grab my little blue potentiometer, and I'm going to connect the top leg to the capacitor and the bottom leg to ground on my circuit. So my capacitor's legs are kind of touching each other, so I'm just going to separate those a little bit. And then I'm going to pop this in there so that the top leg is connected to the potentiometer. And then I'm going to need another cable to get from, let me grab this black cable here. I want to get from the bottom leg of this potentiometer over to ground. Remember, everything has to be attached to the ground. So now I've grounded my potentiometer and I've grounded my signal. The rest of my signal is going through my resistor, through the capacitor, and into the potentiometer. Now I'm going to get my two probes. The black probe I'm going to put into ground because it's always grounded to the other wires, right? So I have my probe, I have my potentiometer, I have my signal all grounded. First thing I'm going to do is take my red probe and I'm going to put it in the same row as the capacitor and the potentiometer. I want to make sure that I'm seeing the full signal. So we're not turning this just yet. And now I'm going to take my cable. Let's see if I have better luck this time around. And we'll just refresh this page, see what we get here. right, we've got everything. I think we might just be in a bad cable. This was working earlier, but oh well. Let's go back to the mode. Seems to be better success anyway. Might actually be this little jack that's giving me problems. I'm going to switch back to the other jack. Yours should be better than mine. Sorry for all of the tech problems. All right. Come out a little bit just so you can see what's going on here. I'm going to bypass the jack, and we're just going to see if we can get some signal. All right, so we're back to our square wave. I'm just going to do this for the rest of this lesson. If you have problems seeing a signal from your phone, you're probably having the same problems as me. I think it has to do with this guy, who is temperamental. So let me know if you have any other way to generate a sine wave out of a computer. Use that. The website is probably the best way to do this. So this is going to be a little bit different, but what I want to show you is basically I'm not going to be able to adjust this amplitude. What I would like to do, though, is I want you to follow these instructions before you move on. You're going to do the following in order. You're going to turn on your scope, you're going to set the coupling mode, and you're going to attach the red probe at the point where the capacitor meets the potentiometer and the black probe to ground. All right, check. We did all those. We're going to play a sine wave on your phone or laptop. I'm going to use my square wave. And we're going to adjust these so we can see the full waveforms on the screen. I want to see like 2 to 3 waveforms. Then we're gonna move to the milliseconds menu and adjust so we can see 2 to 3 waves, and then adjust the volume on your laptop or your phone so that you have an amplitude of 1 volt. So this might be what I can't show you. However, I was able to do this earlier today, and this is what you should see. You'll notice in the bottom left corner, I have 1 volt. It's a sine wave. It's going from the top line to the middle and then down to the bottom line. I have 1 volt up and 1 volt down. Once you are able to see this, I want you to snap a photo. And you're going to post that in your blog. Then, we're going to move the red probe to the center of the potentiometer. So, I can demonstrate this. I'm going to pull out my red probe, which is currently plugged into the top pin of my potentiometer. I'm going to move it down 1 row to the middle. Now, what I've essentially done here, because the top of my potentiometer is connected to my signal, the bottom is connected to ground, I've created a voltage divider. I'm going to turn this, and I can actually make my signal go from max voltage all the way down to basically nothing, right? And I want you to take a video of you doing this. I would like to see your signal go from max voltage down to nothing and then back up again. So, record a video as you turn the potentiometer so the wave goes from max amplitude to minimum and back again. Make sure everything is set correctly according to the above instructions. So basically, you're going to set everything to see this as your original signal. You're going to move the wire to the center of the potentiometer on this circuit. You'll see part 2, the red probe goes here in the middle, and then turn the potentiometer up and down to see the waveform grow and shrink. So, if we were in the lab, what we would have you do is run this exercise on all the different models of oscilloscopes that we have in the lab. Because we're not going to do that, I'm going to let you do a little bit of a research assignment. First, you're going to explain to me about oscilloscopes. You're going to explain every control that you had to set, what it does clearly as if you're teaching someone. You're going to explain the X and the Y axis and how they relate to Sen 1, Sen 2, and the milliseconds options. You're going to explain what the trigger control does. If there's anything else worth mentioning about how to connect your circuit, probes, please include that. So, similar to what you did with breadboards and multimeters, you're going to explain oscilloscopes to someone that may have never used them before. I also want you to explain what you see as you turn the pot in electronic terms. What are the minimum and maximum amplitude of the output waves as a percentage of the input wave? So output wave is part 2, input wave is part 1. What is happening to the voltage as you turn the pot up and down? So, next part. In the NYU lab, we use analog oscilloscopes made by B&K Precision and Tektronix. There's 3 different models. What I would like you to do is find a video online of someone using a professional analog oscilloscope. Basically, if you just say analog oscilloscope, YouTube, how-to video, you can find a basics, how does an analog oscilloscope work. I want you to watch one of these, and what I want you to do is paste the video here. Don't everyone use the first link. You might even want to Google these companies and see if you can find a tutorial. But I want you to identify some differences about how the oscilloscope in the video that you found differs from the ones we're using for this class. Identify at least 3 things that stand out. Now, these could be as simple as, well, adjusting the volts is a knob, not a switch. It might be complicated, like there's features on this thing that aren't even on ours. I don't know what is going on. I want you to watch a video and identify at least 3 things. Second part. In recent years, digital oscilloscopes have become more popular. That's what we have. We have a digital oscilloscope. I want you to find a video of someone using a professional digital oscilloscope. So same thing to what I did over here. I could search for digital oscilloscope. And I want to make sure that you find a digital oscilloscope. You can probably tell because the screen is going to look more like an LCD screen rather than like that old school CRT screen. You might even find a video of what is an oscilloscope, analog and digital. There's lots of resources here. I want you to do the same thing. I want you to copy that video to your lab report and identify some differences about how a digital oscilloscope differs from the ones we're using. And then I want you to identify some differences between an analog oscilloscope and a digital oscilloscope. So you can read some blogs, you can go on some Reddit forums, see what people are saying. All of the scopes at NYU are analog oscilloscopes. The ones that we are using are digital, and they're very, very cheap, but there are a range of oscilloscopes, both analog and digital, and I want you to do a bit of research into the differences between them. So, part 2, this is going to be a research assignment. I want you to dig in a little bit and watch some more oscilloscope videos and write about what you find. So we're going to be using this little red oscilloscope for most of the labs, and it is not as advanced as what they have at NYU. So what I wanted to do for the second part of this class is give you another option for analyzing circuits, and that is using some free online circuit editing software. So we're going to talk about simulating circuits using Multisim. So what you're going to do is you're going to go to multisim.com, and I am logged in here. Let me see if I can open an incognito window just to show you what this looks like. Let's see. Are you even here? Maybe I can't show you. In any case, you will see up here, instead of hello, Mark Cleve, you'll see log in and sign up. So there's a button that's sign up for free. You're going to tell them you're a student, and they'll be able to give you an account. And, you know, we went back and forth in circuit editing software, and last semester when we went online, this turned out to be the best place to build online circuits. It's free, and it's made by National Instruments, which is the company that made all those calculators back in high school. So it's legit, and we're going to use it moving forward to simulate some of these circuits. So I'm going to go up here now that I'm logged in to create circuit. And it's going to initialize Multisim Live. And what I basically get here is like this grid with some things over here on the side that are parts. And then up here, I have a little play button. This says interactive, which I'm going to leave on here, but there's a couple other options for how the circuit operates. And then I'm looking at the schematic. I can also look at the grapher, which I don't have any data yet, so there's nothing going to be in here. And then split screen is going to show me both. So first, let's build our schematic, and then I can open up the grapher, and we can see what we see. So basically, what I'm going to do here is build a simulation of the above circuit. So we're going to use an AC voltage source to simulate a sine wave, set it to 1 volt peak and 440 hertz. Okay, so let's do that. I'm going to open up this menu, and I'm going to do an AC voltage source. And I can just place this kind of anywhere on the screen. And if I double click on it, I get a little menu over here. I can give it an ID. It just defaults to 1 volt, so that's pretty nice. My frequency is 1K. I'm actually just going to change this to 440. And then I don't have to have an offset or a phase or anything like that. As soon as I change it to 440, it pops up there. Okay. Since I'm just recreating this circuit from this class, I'm just going to scroll up and we'll look at it. So what I need next is a resistor and a capacitor and a potentiometer. Let's do it. Open up my resistor menu. I'm going to grab a resistor. I'm going to put it vaguely next to my voltage source. And I'm going to double click it. And I have a resistance of 1K. I'm going to change that over here to 100 ohms. And we're good. And then I'm just going to click on this, and that'll attach those together. Good so far. Now I'm going to go to that same menu. I know this is a resistor, but there's capacitors in here because they're sneaky. I'm going to grab a capacitor. And I'm going to place this down, and you'll notice this capacitor has 2 straight lines. And if I look at my circuit over here, my capacitor actually has a positive and a negative side. I need to know that the resistor is connected to the positive leg and that this little curved leg is negative. So the trick with capacitors, which we're going to talk about in a couple weeks, is that smaller capacitors are not polarized. They're just like resistors. You can flip them around. It doesn't matter. Larger capacitors are polarized. So what I'm going to do here is, while I have this open, first I'm going to change this to 10 microfarads. But then I'm just going to drop down this symbol menu, and I realize my face is kind of in the way, but if I scroll to the right, I will get the capacitor symbol that I want, right? And so now I will connect these two together. All right. So we've got our voltage source, we've got our resistor, we've got our capacitor. Let's grab our potentiometer. Also in the resistor menu. And I'm actually going to flip this around because I want the center of my potentiometer to be on the right-hand side. Just going to turn that around a couple times. And I'm going to connect the top of this to my capacitor. And then I'm going to connect the bottom all the way over here to my voltage source. Now, Multisim doesn't know this is ground, so what I can do is actually click on this little ground icon, grab a ground, throw it anywhere on this bottom line, and now, nope, let's try that again. I'll just draw a line. So, there we go. All right. If I drop it on there, then it just knows that whole thing is ground. Now, what I want to do here is I want to analyze 2 points of my circuit. And the way I can graph them is using this V bubble. I'm going to grab one, and I'm going to identify it as a voltage. And I'm going to just look at this point right at the top of my sine wave. Now, this little menu over here, I'm looking at an instantaneous interactive simulation, right? This is what I want. And if I scroll down, well, my face is kind of in the way. You'll see that it says show plots, and this is checked. And this is the color, it's green. So, move that back into place. So basically, I want to make sure that this is getting plotted. And if I go over to my grapher, I still have to hit play. But if I hit play here, up in the top left, it's going to load my simulator. And here is my 440 hertz sine wave. You'll notice on the vertical axis, I have 1 volt. I have another volt. If I put my mouse over the vertical axis, I can actually make it, I can drag it up and down if I want to. My edge detection for my trigger is on the rising edge, which for us, it doesn't really matter. My trigger, notice there's none. If I set this to auto, now my wave stays still. Just like the trigger on the oscilloscope. I had no trigger and it was just moving. As soon as I set this to auto, and you'll see up here, there's another drop-down menu I can also use. As soon as I set this, my wave freezes in place and I can look at it. So that's fine. That's my first voltage point. I also want to look at my potentiometer. Notice my potentiometer is set to 50%. I can adjust this. I want you to pick an arbitrary value. Not 0, not 100, but I want you to use some value of this R2. And then what we're going to do is we're going to map this point. Now my simulation is still running, so I can't edit my schematic, so I have to hit stop up here. And I want to get a second voltage point. Now here's the trick here. This is a little confusing. My second voltage point is fine. It's also an instantaneous simulation. It's blue. But I can't actually attach it to this point. And it doesn't have its own point, so I can't actually connect it with a wire. So what I have to do is actually go into this ground menu, and I'm just going to get a junction. This just is an arbitrary point that I can attach my line to. I'm going to drop that right there on the probe, and then I can attach it to the middle of my potentiometer. Now you'll notice these say out of date, right? And that's because I've been editing this circuit. So if I press play, now I get new voltage measurements here. So you'll notice that even though I'm not looking at the graph, my voltage is being measured in real time on both of these probes. And if I open up the split screen, now I've got my wave. Because I turned my potentiometer to 25%, I get a wave that is 75% of my maximum, right? And if I wanted to measure this, I would say I'm at approximately 0.75 volts, which is really easy because my peak to peak is 1. So if I'm at 75%, I'm at 0.75. So you should be able to easily determine the peak-to-peak value based on where your potentiometer is. And if I just change this, I should see that wave change in real time, right? So I'm going to close this configuration, and I would like to see a screenshot of this. I'm also going to name this circuit Analog Lab Week 4, and it might get mad at me because I think I already have that as another circuit. And then up here in the upper left, I'm going to click on this menu, and I'm going to say Save As. And I want you to make sure this visibility is public, and this is the name. Yeah, so it gave me another one because I already have one. So I'm going to say this is Lab 4 for Analog Lab. You can write whatever you want here. You can tag it. I'm going to say OK. And now what I'm basically going to get here is a unique URL. I'm going to copy this, and if I paste this into a new tab, then I should be able to open this circuit. So, this is how I want you to share this with me. You're going to go through Multisim, you're going to create this simulation, you're going to save it, make sure you're logged in. I don't think you can do this if you're not. And then you're going to copy this link and put it into your lab. So, let's go down. I said set this potentiometer to 50%. I want you to pick any value and tell me what the voltage is. Save your circuit, copy the link, paste it in your lab report, take a screenshot of the split screen, and also include this in your lab report. Just in case something happens and you can't access the site anymore, you will have a screenshot of the circuit. So I want to see that you actually did it. And that's it. That's it for today. Update your troubleshooting notes if anything was wrong. So just to recap, because that was kind of a lot, there's 3 parts to this lab. You're going to learn how to use this oscilloscope. You're going to look at some of these things, sine waves, square waves, noise. You're going to build this circuit, and you're going to look at a probe at the full volume signal, this green probe. You're going to look at this blue probe, which is the volume adjusted signal. And you're going to follow these instructions. I'm going to see a photo of your sine wave with a 1 volt peak to peak. And then I'm going to see a video of that sine wave going to max and min. Then you're going to do, you're going to explain to me about oscilloscopes, tell me what all these controls do. You're going to do some research into other types of oscilloscopes, analog and digital, tell me about some differences. And then you're going to sign up for Multisim. You're going to recreate this circuit, and I would like to get a link so I can visit your circuit and also see a screenshot of the split screen. So it's a lot of stuff this week, but we're going to be using both oscilloscopes and Multisim a lot moving forward. So try to get familiar with both of these things. They're both super important. If you have any issues with either of them, please let me know. This is the first semester we're using these DSO oscilloscopes, so I have no idea any sort of funny things that might happen with them. Obviously, you saw some of my technical issues, which I'm going to attribute to Apple hardware. But if you have issues getting any audio into your breadboard, let me know and we can figure out some workarounds. Okay, that's it. I will see you all in lab this week.